I am going to go ahead and start the recording, and thank you everyone for being here. I do want to talk a little bit about this IP addressing because I want to discuss.
Can I interrupt just a second?
Yeah, go ahead.
Yeah, I just wanted to know whether the course ends on December 4th. Is that when it happens?
No, it's not actually going to end on December 4th. That's the end date for the school. I will continue to keep the course open.
Because I was worried about Thanksgiving.
Yeah. If you, I got 25 people. We really, as far as an actual completed date for this course, as long as you finish before we start our next courses, I'll be happy. And
I'm not taking the next bunch of courses yet. I need some time off. I can't just jump right into it again.
I understand.
So I'm just so it's okay. So if I run into trouble with Thanksgiving, you're saying I got time?
Yes, definitely, definitely. Here, folks, is just the little PDF I did pull up. That did finally pull up. Talks about all the different projects that they have available. So everything from just making an LED blink to 2 LEDs blink, woohoo! And then you go all the way down to making a servo run.
It's a lot of fun.
Yeah, it's a lot of fun. So you can put in input characters, vibration switch, and then if you actually solder circuit board to where you actually do this. So it's a pretty neat little project. And here they're actually having you solder in a circuit, which is kind of cool.
So they're going to add this whole course to Cisco? I mean,
well,
because
this FreeNova is not part of Cisco, but there is an Internet of Things class already in Cisco.
Oh, very good. Very interesting.
Internet of Things, and there's an Internet of Things introduction and an Internet of Things connecting things. There's even an Internet of Things security class.
There's a lot of opportunities.
Oh yeah, you can learn all you want.
It never ends. Right.
Exactly, it never does end, which is good for us. So IP addressing, let's talk a little bit about, we talked about layer 2 addresses, which are MAC addresses, and those are burned into the hardware. So those addresses are in fact not changeable really. Now, granted, I know there are some ways with software to spoof MAC addresses, but for the most part, layer 2 addresses, MAC addresses, are what we call physical addresses. Whereas layer 3 addresses or network layer addresses are logical addresses. And for us, it's IP addressing. So here they're talking about the Internet of Everything, which is now the Internet of Things. And they're talking about all the different devices that need an IP address. As we think about in our home, all the different devices that need addresses. And we really have run out of IPv4 addresses completely. The only reason we are still able to use IPv4 internally is because of private IP addresses, which are defined by RFC 1918. And that is an address or an address space that is set aside. It's a Class A, several Class Bs, and a large number of Class C addresses that are set aside for use. You will notice that we look at IP addresses as what are called dotted decimal addresses. So 192.168.10.10. Computers look at it in terms of binary bits. So this is 8 bits in each octet. And since it's 8 times 4, it's a 32-bit address because there's 32 bits. Now be aware in IP addressing, bits, a bit is the smallest unit of measurement. So it's like a digit in our numbering system from 1 to 10. Our numbering system 0 to 9 in a base 10 system. In a base 2 system like this, the 2 digits are 1 and 0. So it's either on or it's off. No problem, Pamela, go ahead. No problem. And so the big thing here we want to look at is, do we understand how to do conversion between the two? Because we will have to do this. Now there's a video here I'm going to let you watch. But when you're converting, it's really not that difficult. So you can convert from one to the other, and that is something you'll want to be able to do for the CCNA, okay? You'll notice when you're doing this, the dotted decimal, the way we convert to binary is by the subtraction method. So we'll look and we'll try to figure out, this is base 10. Our base 10 system of 1,234 is 1 1,000, 2 100s, 3 10s, and 4 1s. We don't think of it this way because it's just not something we normally do. We don't consider, we don't even think about it. It's just something that comes naturally to us. Whereas when we start doing base 2, it's a little more difficult. Okay, so I can't, let me see if I can get my marker to work here. I may have to go over here and pull something. I'll do that in a minute. All right. So base 2, instead of using a base 10 system where there's 10 to the 0, 10 to the 1, 10 to the 2, and 10 to the 3 in these positions, we have a base 2 system where it's 2 to the 0, which the value in that position is 1, 2 to the 1, the value is 2, 4, 8, 16, 32, 64, 128. So as we look at these, we can figure out the values by looking at what bit positions are turned on. So if it's a binary number 1, 1, 0, 0, 0, 0, 0, 0, what you do is you just add those positional values up. So 128 plus 64 gives you 192. So this octet right here is equivalent to 192 in decimal. So if we want to go from binary to decimal, we use the addition method. Now, if we want to go the other way, we're going to use another method called the subtraction method, and I'll show you that in a second. But imagine if this was 1, 1, 0, 0, 0, 0, 0, 1, then the decimal becomes 193. And that's one thing you will learn, that anytime the 1 position is on, you have an odd number. Anytime the 1 position is off or has a 0 there, then you have an even number. Likewise, if this is 1, 1, 0, 0, 0, 0, 1, 0, you just add 2 more to it and be 194. One of the things you're going to learn is if the first bit position is on and nothing else is on, it's 128. If the first 2 positions are on and nothing else is on, it's 192. First 3 is 224. First 4, 240, then 248, 252, 254, and if all of them are on, it's 255. So the value in an octet can be from 0 to 255 maximum. Again, if we have binary going to decimal, you just add them together. So you got this on, just like this one here in the next example, the next octet, we would go, all right, 128 is on. All right, 32 is on and 8 is on. So we add those together, and that's 168. And the next one, by the way, I'm going to cheat a little bit because it's 1, 2, 4, 8. So I know it's 8, 9, 10, 11. So I just go, it's 11 because I can add those together. And then this last one here is actually 10 because it's 8 and 2. Boom, 10. So this binary, 32 bits, can be represented as the IPv4 address 192.168.11.10. Here's the great thing, we have an actual binary to decimal conversion activity. So we look here. Now on this one, let me show you a trick here on this one. So this looks like you'd add 128 to 64 to 32. You could do that, but you could also do this. You know that if all the bits are turned on, it's 255. So the 2 and the 1 value are not turned on. So subtract 3 from 255, and that gives you your answer of 252. Not 525, 252. And you can check it. Correct. Then you can get a new number. And you can just keep getting new numbers and practicing. So like here, that's 128 plus 32, that's 160, 162. Boom. So just keep doing it, and you can go through and do that. So this one's kind of funny because this is what's called instead of a byte, it's a nibble. It's 4 bytes turned on. So this is 15. And I just know that because when the last 4 digits are turned on, it's 15. So you will learn these things the more you work with binary and the more you play with it. Now, if you want to go from decimal to binary, now let's go back again. Remember, if it's binary to decimal, you just add the positions together. But if it's decimal to binary, you subtract. So you'll say, okay, I got a value. Can I subtract 128 from it? If the answer is yes, put a 1 there, subtract 128. If the answer is no, put a 0. Okay, so we'll go here and say then you say, can I subtract 64 from it? Yes or no? If it's yes, put a 1, subtract it. If not, put a 0. And you go down through every single one of the different positions until you do that. And that's how simple it is to go from decimal to binary. So let's look at an example here. So 192, is it greater than 128? The answer is yes. So we'll turn on that position and subtract 128 from 192. That leaves us with 64. And we'll say, is 64 greater than 64, greater than or equal to 64? The answer is yes. So turn it on. That leaves us with 0. And then we'll just put zeros all the way down through the rest because there's no reason, you can't subtract anything else. The next one, okay, is 168 greater than 128? Yes. Subtract it, leaves us with 40. Now, is 40 greater than or equal to 64? The answer is no, so you put a 0 in the 64 position. Go to the 32 position, the answer is yes, put a 1 there, leaves you with 8. 16 is too small, so 16 does not fit that, so 8's left over, so you know 16 is going to be a 0 because you can't subtract 16 from 8, but you can subtract 8 from 8, and that will give you your 101010000, which is 168. And that's the process. You go through that process to do decimal to binary conversion. Questions about either one of those, Lena? Okay. All righty, so I'll move on here. Now, one of the things that is important to note is that all IP addresses have a network portion and a host portion. Now, sometimes you'll see it regarded as there'll be a network portion, a subnetwork portion, which is optional, and a host portion. But either way, there is always going to be that in an IP address. The way we determine which part is the network and which part is the host is the subnet mask. A subnet mask is used to be compared against an IP address to determine what portion is the network, what portion is the host. For us, ones in any position on a subnet mask means that that is a network bit. So when I look at this particular mask, 255.255.255.0, that tells me that the first octet is all ones. So the first octet is a network octet. The second octet is all ones. So for the subnet mask, so that octet is a network portion. The third octet is all ones. So that is a network portion. And finally, the last octet's all zeros. So this is the host portion of the address. So I can say that the network that this particular host is on is 192.168.10.0, and its host number is 10. We can also get this by looking at the mask this way, or we can get it by doing the following. If you ever want to know what address or what network a particular IP address is on, what you can do is you can AND the IP address with the mask, and the network portion falls through. Now, ANDing, we'll talk about it in a minute, is a process of basically a 1 and a 1 is a 1, a 1 and a 0 is a 0, a 0 and a 1 is a 0, and a 0 and a 0 is a 0. So the only way to get a 1 is a 1 and a 1. So if we ANDed these together, all of this, we would end up with 192.168.10.0. And that honestly is exactly what your PC does every time it goes on the internet. It takes its IP address, converts it to binary, it ANDs it to the mask, and it determines what network it's on. It then looks at the IP address that it is going to, the destination IP address, ANDs it to its subnet mask, and if it matches the address that it found that it is on, then it knows it's a local IP address. If it doesn't match, then it knows it's remote, and it will send it to the default gateway. In this case, we know that this 192.168.10.10 is on the 192.168.10.0 network. We got a little example here, a little activity you can do, and a good one for your students. And then we look at the prefix length. Now, prefix length is just how many ones are in the subnet mask. So if I do a /8, that means the first octet is all one. So it's 255.0.0.0. /16 is the first 2. and all the way down. Now you're going to learn these other ones here, the 0, 128, 192, 224, 240. These are all subnetted networks that we'll talk about. So when we look at a particular network, okay, we're going to look at a host address, and we're going to know that it is the unique address assigned to the host. Now, the host portion of an address can never be all ones and all zeros. Okay, it can't be all ones or all zeros. The first host address is the first host portion that does not have all ones and zeros. Okay, the last is not all ones or zeros, but now the broadcast address is all ones in the host portion. So let's show an example here. So, for example, this network 192.168.10.0. This network, you'll know that this is the network address because all the host bits are zeros. The first usable address is .1 because it's the first one where it's not all zeros. The last usable is .254 because it's the last host address where there's not all ones or all zeros. And the broadcast address for this network is all ones or 255. So if it's all zeros in the host portion, it's the network address. If it's all ones in the host portion, it's the broadcast address. Does that make sense? Okay. Now showing you here again just examples of how there's not all ones or zeros in the host portion, so it's a valid IP address to be used. Now this is not, that's the broadcast address. It cannot be assigned to a host. That would make anything sent to that 255 would go to every host in the network, or be destined for every host in the network. Okay, we've done those. So assigning IP addresses, I'm going to skip that because I believe you're fairly confident in that. We've talked about unicast, broadcast, and multicast. We've talked about those. Now this is important, public versus private. In our real world today, we do have private IP addressing, which is RFC 1918 addresses, and they are 10.0.0/8, 172.16.00 to 172.31.255.255. So that's a range of class B addresses that are available. And then the entire range of 192.168.0 to 192.168.255 are available. These cannot be routed on the internet. So this is why when you look at your local home router, they're using one of these addresses. It's also why your school probably is using a 10 network or a 172 network for its IP addressing, because they can use those. What happens is at the exit point to your network, your addresses are getting NATed, or network address translated to real addresses. Okay. Here's some other ones. 127.0.0.1 is the loopback, where you can ping and make sure it's loaded locally. 169.254 are the ones used by PIPA, Microsoft's automatic private IP addressing. So if you ever see a machine that has a 169.254 IP address on it, what's probably happened is it's tried to find a DHCP server, but it's been unsuccessful. So it gives itself an IP address in the 192.168.254 at network space. And then sometimes you'll see the 192.0.2 network is used for testing and teaching purposes. Now, the good and the bad news about IP addressing is IP addresses have been in the past assigned to what is called classful addressing. So in other words, we've got a block of addresses from 0 to 127, which are /8. Now, if you look at this mathematically, anything from 0 to 127 has a 0 in the first bit position. So this is how they determine class A addresses. Anything with a 0 in the first position is a class A. And these are very large networks. So they are, the first 8 bits are the network portion. The next 24 bits are the host portion. So they allow for almost 16 million plus, or they do allow for 16 million plus hosts on each network. That's not a very useful network in terms of overall use unless you subnet it, but it is a large number of addresses that can then be subnetted, which is why many people use the 10 network as their internal address. Class Bs are all networks from 128 to 191/16. So you'll notice that if it's a 10, that is the range 128 to 191, because if it's 11, it would be 192. So these are called Class B networks, where you've got network, network, host, host, and these are typically about 16,000 networks of 65,534 hosts. So you notice as we go from an A to a B, there's fewer hosts per network. And then our final is a Class C, which is net, net, net host. So there's 3 octets that are network and 1 octet that is host. And these all begin with 192 to 223, and that is because their leading bit positions are 110. So if you see an address in binary and it's 110, you know it's a Class C, or it's should be a Class C if you're looking at classful addressing. Well, it is a Class C, it's classful addressing. So that's how they got these. A lot of people wonder how they got the number 0 to 127. Well, it's because there's a 0 in the first bit position for everything from 0 to 127. As soon as you go to 128, well, guess what? You get a 1 there. And so for the Class Bs, it's 10, 128 to 191. And then for the Class Cs, it's 110, which is 192 to 223. Because it's 111, it's 224. Now there are Class Ds, which are 224 to 239. Those are a multicast block. And of course, it begins with 1110. And there are Class Es, which are 111, 11110, which is 240 to 255. But Class Es, we don't really work with at all. Now, classful addressing is addressing where every single network is the same size. So when you borrow network bits, they are all the same size. Now, the important thing to realize here is subnetting is borrowing host bits in order to get more network bits. So people ask me many times, subnetting, the definition is borrowing host bits to increase, oops, can't spell, the number of network bits. Because of that, each time you subnet, when you borrow host bits, you increase the number of networks, but you decrease the number of hosts. And then there's also a point of diminishing returns, to where as you borrow more bits, you lose hosts. So you have to be very careful of that. And we'll keep talking about that more as we have folks look over the different things that I put out to different videos. I'm going to skip that part because you can read that. Now, why do we need IPv6? Well, IPv6, well, we're out of IPv4, okay? IPv4 had 132-bit address space. It's done. It's all been used. There are no more IPv4 addresses to give out, which is why we need to use IPv6. It has 128-bit address space, which provides for 340 undecillion addresses, which technically is a single address for every grain of sand on the planet. We will be able to coexist for a while, dual stack. So we'll run both IPv4 and IPv6. In fact, most machines right now are already running, hey Al, already running IPv6 and IPv4. People just don't know it. By default, Windows machines turn on IPv4, IPv6, both. And so it's enabled. Other ways of doing this will be tunneling. So you take an IPv6 network, tunnel it across an IPv4 backbone, and then have IPv6 on the other side for dual stack. Or translation, which is the NAT 6 to 4 and 4 to 6, where you're going to do NAT between an IPv6 and an IPv4 network. Some of this is really the NAT 6 to 4 stuff and all has been really kind of frowned upon. Most people want to go with a dual stack setup. So if you got IPv6 and IPv4 both running on the same devices. IPv6 is a little different. It's 128 bits represented by hextets. So you've got 1, 2, 3, 4, 5, 6, 7, 8 hextets, which gives you 128 bits. So it's 4 hexadecimal digits in each one, but these are hex. So it's a value of 0 to FFFF, and that is all ones in the values there. So when you look at it, these are base 16. So it's 0 is 16 to the first 0 power, 16 to the 1, 16 to 2, 16 to the 3. And as we look at this, you can see how they're actually decimal and binary. So decimal 0, binary. There's hexadecimal for 15. It's F. So if you want to represent 15, it's F, not because there's only with hexadecimal. It's a 16-bit address space, but we've only got 1 through 9, so we have to represent 10 through 15 with letters. The good news is it's really not that hard. 2001 DB800, and there's some different ways you can look at these hex stats. There's some preferred formats, and that means we can actually do some things to kind of make these addresses a little bit smaller. There's some rules we can use so that we don't have to write out this big, huge, long address. The first one is you can omit leading zeros in a hex stat. So if it's 2001 0 DB8, all zeros, that we can actually rewrite that easily as 2001 DB8 0 quad 1s 0 0 0 200. Okay. Now that only applies to leading zeros, not trailing zeros. Has to be leading zeros. So here you see there's 3 leading zeros. Because this is a hex stat, we know there's 3 other zeros there because they've been left out. Item 2, here's another leaving out leading zeros. So 2001 quad 0, just put a 0 there. So same thing. They just go through and show you leaving out the 0. So that's one rule. All right. Rule number 2, you can omit all 0 segments, but you can only omit one all 0 segment with a double colon. So here's an important thing. You'll notice here, this has 2001 DB8 0 all 1s 0 0 0. The easy way we can do this is write it 2001 DB8 0 colon or 1111 colon 200. This tells us we've got 1, 2, 3, 4, 5 hex stats here, and then in the middle of these double colons is 3 hex stats of all zeros. Now, we could not put a double colon here. If we left this 0 out and had 2 double colons, we would know there's 4 different hex stats missing, but are there 3 here and 1 here, or 1 here and 3 here? We wouldn't know. So you can only have one instance of a double colon representing all 0 segments. So again, see, if we did this, you can only use one. So if we got this one and this one, then we can either use colon here or colon here. You can't use it twice. It's not available. So here's a good one. You take this, make it into this. This can become this. This is a very useful one. FF02 colon with all the zeros 1 becomes FE02 colon 1. And we know there's 6 hex stats in here that are made up of all zeros. Here's one we do, and then here's a very interesting here one. This colon 1, which is the loopback for IPv6, it tells you it's just all 7 zeros and then 1 hex stat of 1. And if it's all zeros, you can just do colon. Okay. Next, that's just going through and they have you do conversions, doing the compressed formats. I've got all kind of different examples here you can do. So we can remove leading zeros, and we can use 1 double colon to take the place of multiple hex stats of zeros. Questions about that? All right. Al, any questions?
No.
All right. IPv6 can have Unicast, Multicast, and Anycast. Now, Unicast is 1-to-1. Multicast is 1 to some. And then there's an Anycast, which is best described as 1 to the closest. And we don't really talk a lot about them, but that's the way I describe them, 1 to the closest. Now, what is our prefix length? This is just like a subnet mask. The prefix length tells you how much of the IPv6 address is network and how much is host or subnet. In this case, /64 will tell us the first 64 bits are network. So we got 1, 2, 3, 4 hex stats. And we got 4 hex stats that are interface ID, which are used for the NIC. We do have link local addresses, which is an interesting concept. Every time you put IPv6 on an interface, it will give itself a link local address if you do not assign it. And that is an FFE0 address that you get. And it will be used to have any communication locally. Can't be routed, but it will give it FE80, sorry, FE80. And that will be used just locally, nowhere else. In fact, on most routers, we put on every one of their interfaces, we put the same link local address. So if this is router 1, this would be FE80::1. This would be for link local. This would be FE80::1 link local. Likewise here, so that every one of them has the same. And then router 2 would have FE80::2 for their link local. Right here with this one. You just have to make sure that the router connected here would have FE80::2 or 3, whatever you want to put on it. And that's used for your local exchange of routing tables. It's also used for router, we'll learn about solicitation messages and those types of things as we move along. Now here's a global address. Now global address is routable. And one of the things that makes really IPv6 so easy, especially the subnet, is because they're going to give you 48 bits and then there's 16 bits for the subnet ID. So the great thing about the subnet ID is it literally is subnet 0 to subnet 65.535.534 because you've got 16 bits there to work with. So in this case, you've got this portion is the network, and then the /6410 would be the global address. And of course, you've got : here, you've got the other hexstats that are there. If you put an 0001, it's on subnet 1, literally subnet 1. The wild thing is, though, you can have subnet 10, but subnet 10 is 000A. Or if I say use subnet B, then I literally mean use 000B, because B is subnet 11, and that is an address that can be used in IPv6. So if you see that somewhere, don't get confused when I ask for a subnet of A or subnet of B. So we can put a static IP address on an interface. You go into interface, do IPv6 address, 2001 DB8 ACAD:1, : /64. So on this network, this is IP address 1. 2, and still the true though that every single global port will need a global address. Okay, now the link locals could be all the same, but these global cannot be. This is putting it onto a PC. Notice we put the prefix length and the default gateway. And then we have an example here where we'll do it, and you'll have a lab that you do also. Questions so far? All right, IPv6 address assignment. There's 3 different ways that IPv6 can be given out to a host. There is what's called SLAC, which is stateless address auto configuration, and it will give out prefix, prefix length, and default gateway. And the way this works is the second a machine boots up or a device boots up on an IPv6 network, if it's configured for SLAC only, it will literally say, hey, I'm on this network, so it sends out a router solicitation. I need information about what network I'm on, what prefix it is, what prefix length, and the default gateway I need. They will then, the router, if they're designed to send out router advertisements, will send out via Slack, all right, here's your prefix, prefix length, and default gateway information. The problem here is you notice it doesn't give out DHCP, DNS information like DHCP does. So we have problems with just Slack. It'll give us connectivity, but it won't give us full IPv6 connectivity because we don't have our DNS information handed out. You can also configure your routers to be what are called Slack and DHCPv6, which means it will give out the information that is needed for Slack and will also refer the host to a DHCP server. So it'll go out and say, okay, I'm going to use this address, you need to use this prefix, this length, and this default gateway, but you also need to go over to this server to find your DNS. and the host would then go over there. Okay, so this is just pure Slack. Host just grabs an IP address, figures out what the default gateway is because the router gives it to it, and knows what its prefix length is. This is a case where the client has used a method called EUI64, or more likely this day and age, and because EUI64 uses your MAC address, a random 64-bit number will be used. It creates its own interface ID. If you use an option 2 or Slack with DHCP, you still get the same information you get from Slack. So you still get prefix length, default gateway, but then it says you need to also go over here to get your DNS information. Then the machine will go to the DHCP servers, or DHCP server, and get DNS, domain name, those types of things. Anything that's not being handed out by the Slack router, the router doing Slack, stateless auto configuration. The final way is for router advertisements not to even be turned on. Okay, now, by the way, here's the EUI64 process. I don't know why I didn't do this in the very first thing, but if your client uses EUI64 to create a random interface ID, it does the following. It goes in and says, all right, I take my MAC address, split it in the middle, add FFFE, and then flip the UL bit. So if the bit is 0 and it's the 7th bit, if it's 0, flip it to 1. If it's 1, flip it to 0. Okay. Now here's the problem with this. Since this contains my entire MAC address, what can you do with a MAC address? Does anybody know? You can identify an individual host via its MAC address. So if the MAC address is being used to create the network ID, interface ID for an IPv6 address, you can be easily tracked by, let's say, a government that may not want you to be speaking out against it, or anybody. So for privacy concerns, most operating systems have stopped using this process, okay? And they now use a randomly generated 64-bit number. But if you see FFFE in the middle of it, that means it was EUI generated, EUI64 generated. This is a random number. Okay. So, link local addresses, IP, this is when we go in and that's again creating a dynamic 64-bit address. You see here there's FFFE, that's using EUI, this is dynamic. And then you have link local addresses, FE80, this is using the EUI to create the local EUI64. Most time on our routers, we're going to set our link local addresses. So that's what we do here. So we can go into link local on R1, we go to every single interface and set it FE80:1, because that's router 1. On router 2, all of its link locals will be FE80:2, and 3, 4, so on and so forth. That's why you don't have, there's a couple reasons for that. One, so when you're trying to ping on the link locals, you don't have to type that big, huge, massive IPv6 address. And also, you know what the link local is for that local machine. So how do we verify addresses? IPv6, show IPv6 interface brief. In fact, 99% of the commands, you just put an IPv6 in front of it. Show IPv6 route, ping, and put the entire address in. There's no way around that, unfortunately. Okay, and let's see, a little bit really that's same. This is looking at the router advertisements and router solicitations. That's where we're talking about this. I just booted up and sent a router solicitation to request a router advertisement. And that is via ICMP-v6. So it's a router solicitation saying, hey, I need to know my information. Depending upon whether or not it's doing option 1, which is Slack only, option 2, which is Slack with DHCP, or option 3, which is DHCP only, will determine whether or not the router will send back a router advertisement and what will be in that router advertisement. You can also do neighbor solicitation to make sure that no one is using the address, your own address there. That's kind of like the ICMP duplicate address detection, DAD detection. So And same thing here, DAD. Pinging just tells you that something's up and running. I think we talked about that. This one is neat, but it doesn't work everywhere. Traceroute. Traceroute sends out an ICMP echo request with a hop count of 1. It'll go across the first router, then come back. Then it'll send it with a hop count of 2, go across 2 routers, come back. The problem is it relies on ICMP, and many networks block ICMP at the edge. So many times traceroute will not work when you're trying to test things. It should work internally, but it's not going to work externally. All right, any questions on chapter 7? Al, I asked Lena and I asked Sharon, have you had a chance to watch the videos I put out about subnetting that I sent to the class?
I have not.
Okay, I want y'all to watch those first before we go over this chapter. I don't want to try to get in here and do this and have you not have any background at all. So I want to make sure you've read this chapter, chapter 7, chapter 8, and I want to make sure that you've done those, and then we'll do it next week, okay?
Sounds good. Sounds good.
You good, Lena? You okay, Al? Is that good for you?
Yes.
Yeah, I'm gonna definitely go over those things. And now I have a quick question about the subnetting.
Go ahead.
Now, is a lot of converting going to be on the actual test?
No. You just more than likely you may get something to ask you. Tell me what address is this particular IP address, or what network this IP address is on. So it's really going to be more possibly doing ANDing than anything else. So you'll have to convert it to binary to do the ANDing, but other than that, there won't be a great deal of conversion.
All right, thank you. Good to know, because I kind of really have to listen to all the videos and probably more on YouTube before to understand. Or
well,
is it
in chapter 7, those activities that let you just continue to do multiple conversions, those are really good. They'll help you a great deal. So.
Okay, and that would be in Packet Tracer or the lab?
No, that's actually in the curriculum itself.
Okay, so as I watch videos, they'll give us things to do to convert.
Okay. It's in the actual curriculum. So.
All right, thank you.
Uh-huh.